We all think we know wood, right? It's everywhere. Our floors, our furniture. It's ancient, it's solid, it's reliable. But what if I told you that this super familiar material has been hiding an incredible secret? A superpower, really, that engineers are just now figuring out how to unlock. And it could totally change how we build, well, just about everything.
Okay, so it all starts with a problem that every woodworker, or honestly anyone who's ever had a wooden door that sticks in the summer, knows all too well. Wood moves. It kind of breathes with the humidity in the air, swelling up and shrinking down. And as this quote gets at, that constant tiny movement can be a real headache, warping and cracking even the most beautifully made things.
For basically all of human history, we've treated this as a flaw, something to be managed or fought against. But here's the big question that's sparking a revolution in material science. What if we could harness that incredible internal force? What if we could actually program wood's natural urge to move and turn its biggest weakness into its most powerful feature?
So how on earth is this even possible? Well, it's not magic. It all comes down to two really fundamental properties that are just baked into the very structure of wood itself.
So the first principle is a mouthful. It's called hygroscopy. But the idea is simple. Just think of wood as a super dense sponge. Its cells are literally designed to move water around. And even after a tree is cut down and dried, those cells keep doing their job, sucking up moisture when the air is humid and releasing it when the air is dry. And that process makes the wood itself physically swell and shrink. Now here's where it gets really cool. That swelling and shrinking, it doesn't happen evenly in all directions. Wood is anisotropic, which is just a fancy science word for saying it has a grain, and its properties are different depending on which way you're looking at it. And this, right here, this is the absolute key to controlling how it moves. And check out this difference. It is dramatic. If you look along the length of the grain, the direction the tree grew, wood is incredibly stable. It barely moves at all, like 0.1%. But across the grain, whoa, it can swell and shrink by almost 10%. That is a massive, powerful difference in movement packed into a single piece of material. And that difference, that's everything.
So here's the whole secret in a nutshell. 1, wood is a sponge. And 2, it's a sponge that basically only swells in one direction. The Branching Out Wood blog had this perfect analogy. It's like a garden rake getting wider when you pile on leaves, but it never gets any longer. This predictable, uneven movement is exactly what we can take advantage of.
So once you understand that principle, you can turn this natural quirk into a deliberate, programmable manufacturing process. You can literally tell the wood how you want it to bend, all by itself. The main technique is just brilliantly simple. It's called the bilayer method. So you take 2 thin layers of wood and you glue them together. But here's the trick. You put their grains at a 90-degree angle to each other. And this is crucial. You do it when the wood is wet. So now, as the whole piece starts to dry, one layer is trying to shrink like crazy across its width, but the other layer, with its grain going the other way, is staying totally stable in that direction. What happens? Well, the 2 layers basically fight each other, and this internal tug of war forces the entire panel to bend into a perfect, predictable curve. And this right here is the big breakthrough. We're not just letting wood warp anymore. We're hijacking the warping process. By controlling the grain direction, the moisture, the thickness of the layers, we can program a flat piece of wood to transform itself into a very precise shape with no giant machines or molds needed.
Of course, trying to predict all these complex forces isn't just guesswork. It takes some serious computational firepower. And this is where modern tech gives designers the tools to almost collaborate with the wood itself. See, in the past, if you wanted to predict this stuff, you had to use a super complex process called finite element analysis, or FEA. It's basically breaking an object down into millions of tiny digital pieces to simulate stress. It's powerful for sure, but it's also incredibly slow and takes a ton of expertise. But now, new design tools are completely changing the game, making the whole process intuitive, visual, and unbelievably fast.
So, how much faster are we talking? Well, researchers at Carnegie Mellon developed a machine learning simulator called Simulearn that is over 1,000 times faster than traditional FEA. That's not just a little better, that is a complete game changer.
What that kind of speed gives you is real interactivity. A designer can now tweak a design and see the final shape almost instantly. The computer can even suggest its own modifications to get a target shape. It's basically a creative conversation between the human and the machine. And this kind of co-design process is what makes building these complex, self-shaping things actually practical.
Okay, so we've got the science down, we have the super fast design tools. Now for the fun part. What can we actually do with this? Well, the applications are amazing, and they range from the tiniest little things all the way up to full-blown architecture.
Let's start small. Meet the E-Seed. And yep, you heard me right. It's a tiny wooden robot designed to plant trees. It has no batteries, no wires, no motors, just the programmed intelligence of wood.
The design is actually bio-inspired. It mimics a real seed that literally drills itself into the ground. As the humidity changes from day to night, the three little tails on this piece of oak veneer coil and uncoil, and that motion creates a drilling action that buries the carrier. You could imagine dropping millions of these from the air, each one carrying a seed, maybe some fertilizer, to reforest huge areas of land completely passively and naturally.
Now, at the human scale, you can use this same idea to create these amazing things called compliant mechanisms. These are structures that move because the material itself is flexible, not because of separate parts like hinges. This prototype is a door lock made from a single piece of material. It will only unlock if you move the handle in a very specific sequence. It's like a mechanical password that's been coded directly into its physical shape.
Okay, now let's think bigger, much bigger. Using that exact same bilayer method, we can create large-scale timber panels. Imagine shipping these panels to a construction site, perfectly flat, easy to transport. Then, once they're in place, you don't need giant machines to bend them. You just need the weather. You expose them to rain or just a change in humidity, and they curve themselves into walls, roofs, even entire shelters. It's self-assembling architecture, powered by nature.
What all of this is pointing to is a whole new category of technology. It's not really a hard robot with gears and motors, and it's not a soft, squishy robot either. People are starting to call it firm robotics, devices that use their own material intelligence to respond to their environment. This could lead to buildings with skins that can breathe, opening and closing vents based on humidity, powered by absolutely nothing but the weather. It's a real glimpse into a truly sustainable, bio-inspired future. The idea that one of our oldest materials has these futuristic powers is just astonishing. And it leaves you with this one last, kind of mind-blowing thought. We've spent centuries forcing materials to do what we want. What could we achieve if we just started listening to the intelligence they already have? What other secrets are hiding in plain sight, just waiting for us to understand their language?